A variety of diodes are constructed over the time which are suitable for different purposes. We will discuss three special diodes from where sometimes theoretical questions are asked in state level examinations. One such very popular diode is breakdown diode, which we have already studied, as the other name for a breakdown diode is Zener diode. One misconception students generally has is Zener diodes always has Zener breakdown. However, this is not true. It is not necessary that Zener diodes will always have Zener breakdown, as it depends upon the breakdown voltage. If the breakdown voltage is less than 6 volt, typically Zener breakdown takes place. However, if the breakdown voltage is greater than 6 voltage, then the avalanche mechanism will take place. This is a rough estimate. The diodes are heavily doped so that the reverse bias voltage required for junction breakdown reduces. However, for any type of diode, Zener breakdown occurs at voltages lesser than avalanche breakdown voltage. These type of diodes are used in reverse biasing, as there will be no specific advantage in using the Zener diode in forward biasing, as it would act as a normal diode. Another common type of diode is Varactor diode, which comes from two words, variable and reactor. This specifies the property of this diode of having variable junction capacitance, which depends upon the applied reverse bias voltage. Varactor diode in particular is a linearly graded diode, and we have derived the expression for junction capacitance to be equal to junction capacitance at zero biasing divided by cubic root of built-in potential plus reverse bias voltage. And if the reverse bias voltage is significantly greater than built-in potential, then the junction capacitance will be inversely proportional to cube root of reverse bias voltage. One major challenge for every electronics engineer is to fabricate as many as electronic components that can be designed in a single chip. More layouts are continuously designed and improved so that more number of electronic components can be fabricated on a single chip. For example, Varactor diode can be used in tuning stage of a radio receiver to replace the bulky parallel plate capacitor. The size of the resulting circuit is greatly reduced and its dependency is also improved. Last diode is tunnel diode, which is also named as Esaki diode after its inventor Leo Esaki. As the name signifies, the operation of this diode is based on tunneling mechanism, but the most important property that it exhibits is of negative resistance. We know that xenon diodes are heavily doped, but if we compare tunnel diode with xenon diode, then tunnel diodes are extremely heavily doped, and we know that such type of diodes are called as degenerately doped diodes. Due to the extremely large doping, the reverse breakdown occurs at very low voltages. To understand how it has negative resistance, we have to consider an energy band diagram. You should recall that for a degenerately doped n-type semiconductor, the Fermi energy level lies in the conduction band, whereas for a degenerately doped p-type semiconductor, the Fermi energy level lies in the valence band. The shown energy band diagram represents the p-type and n-type region are very heavily doped and has a narrow depletion width, which ultimately facilitate the tunneling process. In equilibrium case, the Fermi energy level on the p side region coincides with the Fermi energy level on the n side, so that there is no electron flow. Practically, when we bias a diode, two significant changes takes place. One, the depletion width changes. We know that the depletion width is dependent upon the applied voltage. And the second change that takes place is the relative position of the energy levels of the n-type and p-type. However, for our easier understanding, we will ignore the first impact, which is the change in the depletion width. It is not necessary to show the change in depletion width, as it will only complicate our understanding. So, for understanding the mechanism of tunnel diode, we will fix the width of depletion region. We can fix any of the energy levels. Here, we are going to fix the p energy levels and will shift the energy levels in the n region. If the diode is reverse biased, then the energy levels in the n-type region will move downwards. I have recalled this a number of times, and again I am recalling that for an energy band diagram, the points which are at lower position in the energy band diagram represents the higher potential. So we will have to shift the energy levels of the n-type region downwards. Similarly, if the diode is forward biased, the energy levels in the n-type region will move upwards. Now we will consider all the cases of biasing. First is the reverse biasing. In the reverse biasing, the Fermi energy levels has been shifted downwards. As you can see that the Fermi energy level in the p-type and n-type region are not coinciding. But you can clearly see that there are vacant energy states in the conduction band of the n-type region which are directly opposite to electron-filled states of valence band of the p-type region. This will ultimately result in the electron flow from valence band of the p-type region to the conduction band of the n-type region. Electrons are flowing from p-type to n-type, and the conventional current flow will be from n-type to p-type. The case of reverse biasing is very simple, as if we keep on increasing the reverse biasing, more downward movement of n region energy levels will take place, which will bring more number of vacant energy states opposite to electron-filled states of p-type region, which will ultimately increase the reverse bias current. So we can simply say reverse bias current is directly proportional to reverse bias voltage. The second case is zero biasing or the equilibrium case. This case is also very simple. As we already know, in the zero biasing case, the Fermi energy level in the p-type and n-type region coincide with each other such that the net current flow is zero. Now comes the most important case of forward biasing. The forward biasing consists of three cases. The first case is when the forward bias voltage is greater than 0 and smaller than the voltage corresponding to the peak current. Right now, it might be difficult for you to understand the peak current, but by the end of the lecture, you will get the clarity. In this case, you can see the energy levels in the n-type region have moved upward. It can be seen clearly that the vacant states are present in valence band of the p-type region opposite to electron-filled states of the conduction band in the n-type region. Therefore, electrons will try to flow from the n-type to p-type region. Here also tunneling will take place, but opposite to the direction of reverse biased case. The net current will be from p-type to n-type. Now, we have to understand the two extreme points of this particular case. First is zero biasing, and the other is when the forward bias voltage is equal to the voltage corresponding to peak current. The first case we have already discussed, when the applied voltage is 0. The second case is what if the forward bias voltage is equal to voltage corresponding to the peak current. The corresponding energy band diagram will look like this. In this case, maximum number of free electrons in the conduction band of the n-type region are opposite to vacant states in the valence band of p-type region. That's why the current in this particular condition will be the maximum. If the forward bias voltage is increased even a little, then the resulting current will decrease. We will see the second case when the forward bias voltage is greater than the voltage corresponding to peak current and smaller than the voltage corresponding to valley current. See the diagram very carefully. You can see the free electrons in the n-type region does not change, but the vacant states in the valence band of the p-type region just opposite to the energy states of the conduction band occupying free electrons have been reduced. And obviously, electrons cannot make transition to the states present in energy band gap, which is also having another name, forbidden band gap. Since the number of effective vacant states have been reduced, the net current decreases. This is the most important point of the mechanism of tunnel diode, as this represents how even if we are applying greater forward bias voltage, then also current actually decreases, as the energy levels in the n-type region will move upwards, which will reduce the vacant states in the p-type region opposite to electron filled states in the n-type region. This is the reason why we have negative differential resistance in tunnel diode, and the net current will keep on decreasing until the current reaches to its minimum value, which is referred as valley current. So the next question is, what happens when the forward bias voltage is equal to the voltage corresponding to the valley current? In that case, the energy levels of the n-type region have shifted upwards enough to interact with the vacant states of the conduction band in the p-type region rather than to interact with the vacant states of the balance band. So, if the voltage is equal to the voltage corresponding to valley current, then the electrons will start jumping to the conduction band energy level in the p-type. Therefore, the net current will begin to increase from this point. At the voltage corresponding to the valley current, the net current is minimum. If we increase the forward bias voltage further, the current will begin to increase. The third case of the forward biasing is when the forward bias voltage is greater than the voltage corresponding to valley current. As the energy levels in the n-type region move upwards, more number of electrons are able to interact with vacant states of the p-type region conduction band. Therefore, more number of free electrons will be able to flow from n region to p region, increasing the net current. When the voltage is greater than the voltage corresponding to valley current, the tunnel diode actually acts as a normal diode. Here we have the characteristic voltage ampere graph of a tunnel diode. I hope this is easily understandable to you. This graph is one of the most important graphs of the study of electronic components. You can observe when the tunnel diode reaches its maximum current, that is peak current, and if we still increase the forward bias voltage, then the current will actually decrease, creating a region of negative differential resistance. And after the valley voltage, on increasing the forward bias voltage, then the tunnel diode will act as a normal diode. I hope you enjoyed the lecture.